Hello class of 2018. Today we're looking at continuous random variables. So we are aiming to understand the properties of a continuous probability distribution. We need to be able to determine if a function is actually a continuous probability distribution, and we can use the rule to find probabilities. So here are some basic definitions. A random variable is a variable whose value is determined by the outcome of a random experiment. And for a continuous random variable, the word continuous means it takes any value. For example, you could have a foot size, and as you know, feet don't come in specific lengths, they come in all sorts of lengths. So you have to round off the length of your foot. And so the same thing applies with continuous random variables, and you can have different types of variables like heights of people, mass of pets, temperatures, you name it. And when you graph them, what are you going to get? You're going to get some x value here, and you'll get probabilities that are not just discrete, but they're actually filled in all in the middle here as well. So there's a whole set of possible values you could have. The most common shape is the bell curve, but you could get other shapes. For example, you might have one that looks like this, and it might be 0 everywhere else. So here are the conditions for f of x being a continuous probability distribution. The function must always be greater than 0 or equal to 0. The total area has to equal 1, and if you're going from negative infinity to infinity, it would be an area of 1. So you might have something like this, which is a bell curve, and for x going from positive infinity to infinity, the area is going to be 1. More likely, you're going to get something where you have a definition of the function between 2 points. So you'll have the function defined between a and b, and everywhere else it'll be 0. And so the same thing applies. The area underneath this section here has to equal 1. What else? We also have probability only defined for a range of values, usually between a and b, and of course that's x, which I forgot to label. And the last thing is that you don't have an individual probability. So the probability of x less than a particular value c is going to be the same as the probability of x is less than or equal to. And the reason for that is because you don't have an area of a single line, which is what that would be. That would be probability of x equaling c. So the final thing to know is that the two conditions for f of x to be a continuous probability distribution are that 1, it's always greater than or equal to 0, and the total area of the curve is 1. So I'll just add that this probability here actually equals 0 because you can't have the area of a skinny line. Now some handy formula you will find useful. The area of a rectangle, for example, you might have a probability distribution defined between 2 and 4. You could also have an area of a triangle. That's meant to be a triangle. And you could also have an area of a trapezium, where that could be the shape of your probability distribution. So here you hope to check that this area should equal 1, same with this one, and same with this one. Now for conditional probability, the conditional probability formula still applies. Probability of A given B is equal to the probability of A intersection B divided by the probability of B. So some hints. The probability of x between A and B, not including A and B, is the same as the probability of x between A and B, including A and B, because x is continuous. And you also know that the probability of x greater than A is the integral under the curve f of x from a to infinity. So that actually looks like this here, for example, for a bell curve. But the same thing would apply for any probability distribution. So that there would be the probability of x greater than a. If the infinity is involved, like here, then you need to use the limits. And basically, that's basically the same picture as up here anyway. It's just that you can't always integrate this directly, so you might have to take a limit, that's all. So here's an example where we are trying to establish if f of x is a continuous probability distribution. This is a definition here, so it's always helpful to do a sketch first. So I'll do a sketch between 1 and 2 for x, which means that's the y-axis there. And if we sketch 4x, that means that it would normally be a straight line passing through the origin, but we only use the bits between 1 and 2. And this point here is the point 1, 4, and this point here is the point 2, 8. Alright, so your first condition, that f of x has to be greater than or equal to 0, is true because it's all positive. The second condition that we need to check is that the integral of f of x dx should equal 1 when we integrate between 1 and 2. Let's see if it actually works. The integral of 4x dx from 1 to 2 is equal to 4x squared over 2 from 2 to 1. If we cancel that down, we have 2 out the front, x squared to 1. And so that gives you 2 times 2 squared minus 1 squared, which is 2 times 3, which is 6, which is not equal to 1. So therefore, f of x is not a PDF. There you go. Whoa. Right, so we're trying to find a value of a so that the given function f will be a probability density function. A little bit of a trick to start with is to substitute in x equals 2 to find the endpoints. So if x is 2, f of 2 is a times 12 minus 3 times 2, which is 6a. And if x equals 4, f of 4 is equal to a times 12 minus 3 times 4, which gives you 0. So a little bit of a preliminary sketch gives us 2, 4, and x. It crosses at 4, and we'll have to have a positive, so that's 2, 6a down here. Now, to do the second part, we have to find an integral between 2 and 4 of a bracket 12 minus 3x dx, and it should equal 1 if it's a probability density function. So we'll just apply our anti-differentiation rules as usual. We have a at the front, then we can integrate or anti-differentiate 12, giving us 12x, and then anti-differentiate 3x, which gives us 3x squared over 2. That's an x, even though it's funny. From x is 4 to 2 equaling 1. So therefore we'll have a bracket 12 times 4 minus 3 bracket 4 squared over 2 minus bracket 12 times 2 minus 3 times 2 squared over 2 equaling 1. A little note, you could actually plug this straight into your calculator and ask it to solve for a. It should do that, but this part here is just us doing it by hand. So if we continue, we have a. Now we sort of do a little bit of a trick here. 2 squared divided by 2 is just 2. So that gives us 3 times 2 over here. So that's 24 minus 6, which gives you 18. 12 times 4 is 48, so 48 minus 18 is 30. And then 3 bracket 4 squared over 2. You can simplify a little bit. 3 times 4 squared, do the 4 squared first. 16 divided by 2 is 8. 8 times 3 is 24. So we have 30 take 24. So therefore 6a equals 1 and a equals 1 on 6. And so for this example, we're trying to find a probability, and we're going to trust that this is a probability density function because it says it is. So we just need to find the probability that x is less than 5. And if I do a little bit of a sketch here, we're going from 2 to 10, and this is a straight line that has a positive slope, so it's something like this, and we only use the bits between 2 and 10. And so we want to find the probability that x is less than 5. It's basically this part here, between 2 and 5. So we want to find the probability that x is between 2 and 5, which is equal to the integral from 2 to 5 of x over 48 dx. If we integrate that in turn, you get x squared over 2 times 48 from 5 to 2. So we get 1 on 96 times 5 squared minus 2 squared, which is 1 on 96 times 25 minus 4, which is 21 over 96. They do simplify, that goes into 3 7 times. 96 is 32, so your answer is 7 on 32. And so here we have a probability distribution function given by f of x equals half x minus 4 between x is 8 and 10, and 0 everywhere else. So finding probability of x is greater than 9 is finding the integral between 9 and 10 of half x. Whoops. Can I undo that? Yes, I have half x minus 4 dx, which is half x squared over 2 minus 4x from 10 to 9. So we have a quarter, 10 squared minus 4 times 10 minus a quarter, 9 squared minus 4 times 9. That gives you 25 minus 40 minus 81 over 4, can't do much about that, plus 36. So then we have minus 40 plus 36 gives you minus 4, and then the 25 minus 81 over 4 is actually 100 minus 81, which is 19. And that gives you 4 3/4. Take away 4, so that gives you 3/4. Now for part B, it's asking to find the probability between 8.5 and 9 of the same thing. So half x minus 4 dx. Same thing again, you can use a calculator to do this for you, or if you do this by hand, you go to half x squared over 2 minus 4x from 8.5 to 9. So we have a quarter times 9 squared minus 4 times 9 minus a quarter times 8.5 squared, which is 17 on 2 squared, minus 4 times 17 on 2, which gives you 81 on 4 minus 36 minus 17 squared on 16 plus 34. So minus 36 plus 34 gives you minus 2. I have to do this little trick here to make everything over 16. And so 81 times 4 is 324. 17 times 17 is 49. 7 plus 4 is 11. 9, 8, 289. So you have 324 take away 289. Take 9 is 5. 31 take away 28 is 3. So you have 35 over 16 minus 2. 35 over 16 is 2 and 3/16. So therefore your final answer is 3 over 16. And so your lucky last one is a conditional probability case. So I actually write this out in full to start with. So I need to find the intersection of x greater than 9 and x greater than 8.5 divided by the probability of x being greater than 8.5. Now, if I do a little diagram on the side here, I have 8.5 and 9. This condition here is satisfied by this circle, which should be centered over 9, sorry. And this one here is x is greater than 8.5. And where they overlap, which is the answer, is the empty circle here, that x is greater than 9. So therefore it actually reduces to x greater than 9 divided by probability of x greater than 8.5. Now, the first bit here of the numerator, you've worked out previously as 3/4 from part A. The denominator has not been worked out, which is annoying. So you'd have to work it out by integrating from 8.5 up to 10 of half x minus 4 dx. And so I've just plugged it into my calculator and got 3/4 over 0.9375, which gives me an answer of 0.8. Right, so the last one here is just asking you to find the integral form and doesn't give you the function. So you just have to rely on your first principles definitions. So we have a conditional probability question, so we have to write the intersection version first. And then I'm going to draw over here the number line with 1 and 2 on it. And so the first case, x is less than 2, is this case over here. The second case, where x is greater than 1, is over here. And so the overlapping section is the holes between them. So therefore it has to be x between 1 and 2, not including the endpoints. Then if you write these in integral form, then it's an integral from 1 to 2 of f of x dx, and the integral from 1 to infinity of f of x dx.